Hello, dear student, myself Dr. Surekha Jaiswal, Head Department of Physics, Moreshwar College, Bhokardan. Today we will see mechanics, properties of matter and sound, semester first, course code number Phy101. Now, today's contents are Bernoulli's theorem, practical application of Bernoulli's theorem containing law of hydrostatic pressure, and second, that is filter pump and Poisson's formula. Now see Bernoulli's theorem. This is a theorem about conservation of energy for a flowing fluid from one end to another in streamline flow. Now when any incompressible liquid of unit mass flows steadily without any friction along certain direction, then its total energy remains constant, and this is called Bernoulli's theorem. This law holds true for ideal liquid having streamline flow. According to Bernoulli's theorem, pressure energy plus kinetic energy plus potential energy equal to constant. So that is P plus half rho v square plus rho gh equal to constant. Now see proof of Bernoulli's theorem. Let us consider liquid is flowing in a tube from position x to y in the figure C. Consider P1 is the pressure of liquid at x and P2 is the pressure of liquid at y. Let A1 and A2, see in figure, A1 and A2 are the cross-section area at x and y respectively. Let H1 and H2 are height of centers of liquid from ground surface. See, H1 is the height at the point x and H2 is the height at the point y from the ground surface of the liquid. Now let V1 and V2 are velocity of liquid at x and y, and W1 and W2 are the work done at x and y. Now here see, due to pressure P1 acting on it, and at the other end if the fluid pressure is P2 and fluid velocity which is coming out is V2, as we know that if cross section area reduces, flow of velocity increases, but say pressure are P1 and P2 and V1 and V2 are the velocities. Now from equation of continuity of flow, A1 V1 equal to A2 V2. Let's in short interval of time dt, liquid moves a distance by V1 dt from x and covers a distance V2 dt from y is due to the force P1 A1 and P2 A2 respectively in the tube. Therefore work done equal to Wx equal to force into displacement, that is equal to P1 A1 into V1 dt. Similarly at the position of y is Wy equal to P2 A2 into V1 dt equal to P2 A1 V1 dt, that is therefore A1 V1 equal to A2 V2. So net work done by the liquid in time dt is given by W equal to Wx minus Wy, that is equal to P1 minus P2 into A1 V1 dt. And this work done on the liquid changes potential and kinetic energy of liquid. In time dt, mass of liquid displaced through the section x is a1 v1 dt rho, and through section y, that is a2 v2 dt rho. So therefore potential energy of liquid at x is a1 v1 dt rho g h1, and here the h2 minus h1 equal to into a1 v1 dt rho into g. So the kinetic energy of liquid with the mass a1 v1 dt rho at x is half a1 v1 dt rho into v1 square, and kinetic energy of liquid with mass a2 v2 dt rho at y is half a2 v2 dt rho into v2 square, so equal to half a1 v1 dt rho into v2 square, and from continuity equation a1 v1 equal to a2 v2, and therefore change in kinetic energy for the mass a1 v1 dt rho of a liquid is half a1 v1 dt rho into v2 square minus v1 square, and so work done on the system by the pressure force is converted into potential and kinetic energy, and therefore W equal to total work done equal to potential energy plus kinetic energy, and therefore using the equation 2 and 3 and 4 we get P1 minus P2 A1 V1 dt equal to H2 minus H1 into A1 V1 dt rho into G plus half A1 V1 dt rho into V2 square minus V1 square, and therefore from this P1 minus P2 equal to H2 minus H1 rho G plus half rho into V2 square minus V1 square. So therefore P1 plus H1 rho G plus half rho V1 square equal to P2 plus H2 rho G plus half rho V2 square. So this equation is applicable to any section of tube having different area. So we can write general equation as P plus rho GH plus half rho V square equal to constant, or P upon rho plus GH plus half V square equal to constant. Now from energy equation we can write total energy of liquid as mass into P upon rho plus mgh plus half mv square equal to total energy, and so total energy per unit mass of liquid equal to P upon rho plus gh plus half v square, and therefore from equation 5 and 6 we can conclude that using this equation 5 and 6 we can conclude that total energy for unit mass of liquid flow equal to constant, and this is called as Bernoulli's theorem. So using this Bernoulli's theorem we can say that P plus half rho v square plus rho gh equal to constant. Now see practical application of Bernoulli's theorem. Law of hydrostatic pressure. Now the pressure exerted by liquid at equilibrium at a given point within the fluid due to the force of gravity is called the hydrostatic pressure. This pressure increases in proportion to depth measured from the surface because increasing weight of liquid exerting downward force from above. Means this pressure increases in proportion to the depth measured from the surface because increasing weight of liquid exerting downward force from above. And this law is stated here: the pressure exerted by a liquid at equilibrium in a given point within a fluid due to the force of gravity, that is a hydrostatic pressure. Now consider a liquid in a tank having density rho. See that tank having the liquid having the density rho, and let A be the point over surface of liquid. See that point that is denoted by A, that is on the surface of the liquid, and having surface of liquid at a distance h1 plus h. See this height is denoted by at the point P, that is another point B denoted, and having the height h1, and from this height is h. So at the point A the height becomes h plus h1 from ground surface. At surface of liquid, pressure is the atmospheric pressure, that is denoted by P.Atm, that is the atmospheric pressure. And let another point is considered as B. See that is another point at a distance from the ground surface, that is a h1, and having pressure PL denoted here. Now using Bernoulli's theorem we can write here PA upon rho plus G into HA plus half V square A equal to PB rho plus GHB plus half VB square, that is equal to constant. Since liquid is not flowing, therefore VA equal to VB equal to 0. At point A, PA equal to P atmosphere, that is atmospheric pressure, and HA equal to H plus H1. So at point B, PB equal to VL and HB equal to HL. So from equation P atmospheric upon rho plus G H plus H1 plus 0 upon equal to PL upon rho plus G into H1 plus 0. So therefore atmospheric pressure P upon rho plus GH equal to PL upon rho, and here therefore after simplification PL equal to P atmospheric plus rho GH, and this is shows that pressure inside liquid increases as depth of liquid increases from liquid surface, and this is law of hydrostatic pressure, that is PL equal to P atmospheric plus rho GH. That law is here shows that the pressure inside the liquid increases as the depth of liquid increases from the liquid surface. Now another application, that is filter pump. Now this pump is used to generate partial vacuum in laboratories. This pump consists of outer enclosure B as shown in figure, in which tube A is connected inside ending with jet A. See that filter pump is consist of a outer enclosure B as shown in figure. See, and here in which tube A is connected. See this tube A is connected inside ending with jet, and another tube D, see that is another tube here D is connected to the other end of its acts as a sink. See in figure, this is acts as a sink, and tube T is here connected at the center of enclosure B as shown in figure. Now if water is forced into tube A due to small opening at jet point orifice, that is a small opening, water is coming out with very high velocity. According to Bernoulli's theorem, as velocity increases, pressure gets reduced at that point and air gets stuck through T inside the chamber B. In this way, the pressure in the vessel is reduced to just a little above vapor pressure of water in very short time. The vessel which is to be evacuated in is connected to the tube B. Here see. See in figure, the vessel which is to be evacuated is connected to the tube B, that is shown in figure, that is a T. The velocity of emerging water is very large and therefore the pressure of the air near the jet becomes less than the pressure in the vessel. Hence, air from the vessel rushes into the tube D and is carried along the water jet, thus partial vacuum created in the vessel. And this pump can reduce the pressure about 2 cm of Hg, and this pump is also called as aspirator. It is used as a backing pump if tube A is not straight but twisted one, then exhaustion produces more rapidly, and this application is used in automobile carburetor to mix air in petrol. Poisson's formula. Now see, for determination of coefficient of viscosity by flow method. Now here consider a vessel to which a long capillary tube is attached horizontally at bottom end. Let length of capillary is L as shown in figure. See here, that is a vessel to which a long capillary tube is attached horizontally at the bottom end. Let length of capillary is denoted by small l and having small radius r. This capillary tube having the radius, that is denoted by small r. At the center of vessel, a long vertical tube is attached for overflow of liquid so as to maintain steady flow of liquid through the capillary. That is here at the center of vessel there is a vertical tube is attached. Now figure B shows, see in figure B shows extended diagram of capillary. That figure B is here, that is shows the extended diagram of capillary with different layers of flow of liquid. When liquid is produced into vessel through inlet tube, then it comes out through capillary tube unsteadily. When liquid rises at the top end of central outlet tube, then excess liquid is coming out through it, and so water level in vessel is maintained and capillary tube flow is now steady but kept very small. When liquid flows through the tube as streamline flow, then it forms a coaxial cylindrical layers of liquid, and the cylindrical layer to the axis moves with higher velocity as compared to peripheral layer, and the velocity of successive layer from center decreases in outward, and the velocity of peripheral layer in contact with inner surface of capillary is 0. Now, the method holds good only when the flow of the liquid is steady and streamlined, and also the tube is horizontal so that the gravity does not influence the flow of the liquid, and the pressure over any cross section remain constant so that there is no radial flow, and also the liquid is in contact with the walls of the tube is at rest, and the liquid is capable of subtending a small shearing stress. Now consider two cylindrical layers of liquid with radius x and x plus dx. See here, the capillary having the here two cylindrical layers of liquid with radius x and another radius, that is the x plus dx of the another layer. Now the velocity gradient between these two layers is dv by dx, and the retarding force on the layer with radius x due to the layer of radius x plus dx is F retarding, that is force of retarding force, that is equal to minus eta A into dv by dx, where eta is called coefficient of viscosity of liquid and A is the surface area of cylindrical layer at x, and negative sign indicate that layer at x plus dx oppose the flow of liquid at x. If L is the length of capillary tube, then area of this cylindrical layer is given by area A equal to 2 pi x into L, and therefore retarding force equal to minus eta 2 pi x into L into dv by dx. The force on layer at x due to the pressure P between two ends of the tube is force retarding force F equal to pressure into circular cross sectional area at x. So force equal to P into pi x square, and so when liquid flows steadily, then F retarding equal to Fp, that is a minus eta 2 pi x L dv upon ds equal to P into pi x square, and therefore dv by dx equal to minus P into pi upon 2 eta L, and therefore dv equal to minus P upon 2 eta L x dx. After integrating, we get integral of, after integration, Vx equal to integral of dv equal to integral of minus P upon 2 eta L into dx, and therefore Vx equal to minus P upon 2 eta L into x square upon 2 plus C1. For the cylindrical layer of liquid in contact with inner surface of tube, is assumed that it is a velocity is 0, that is force for x equal to r and v equal to 0, and therefore using the condition above equation becomes here, that is becomes 0, and therefore 0 equal to minus P upon 4 pi 4 in eta L into r square plus C1, and therefore C1 equal to P upon 4 eta L into r square. By putting the value of C1 in equation 8, we get Vx equal to P upon 4 eta L into r square minus x square. And similarly, velocity of layer x plus dx is given by Vx plus dx equal to P upon 4 eta L into r square minus x plus dx bracket square. When two layers are very closer to each other, then dx is very small and hence Vx equal to approximately equal to Vx plus dx. So volume of liquid d tau coming out per unit volume time t within cylindrical layer x and x plus dx for capillary of length L is given as d tau equal to 2 pi x dx into L upon x, and therefore is equal to 2 pi x dx Vx as L upon t equal to Vx. And using this equation of Vx, d tau equal to 2 pi x dx into P upon 4 eta L r square minus x square, and therefore that is equal to pi P upon 2 eta L into r square minus x square x dx. So total volume of liquid coming out per unit time through capillary tube of radius r is total volume equal to P pi upon 2 eta L into r square integral from 0 to r x dx minus integral from 0 to r x cube dx equal to total volume equal to P pi upon 2 eta L equal into r raised to 4 upon 2 minus r raised to 4 upon 4, and this after simplification total volume equal to P pi rho r raised to 4 upon 2 eta L, and this equation is called Poisson's equation to measure volume of liquid flowing through narrow tube of radius r and length L. From equation we get viscosity of liquid as eta equal to P into pi r raised to 4 upon 8 L into total volume. And to calculate eta practically, pressure is P is measured by using formula P equal to H rho G, where H is the height of the surface from center of capillary tube, and rho is the density of liquid, and G is the acceleration due to gravity of earth, and R is the inner radius of capillary tube measured using the traveling microscope, and L is the length of capillary, and the total volume of liquid collected in a beaker in unit time t, and the total volume must be constant for every interval of time t, and the flow of liquid is maintained streamlined and steady by keeping its velocity very small, and as gravity of earth influences the flow of liquid, so to avoid this effect capillary tube is kept horizontal and there should not be radial flow of liquid. It is assumed that the liquid in contact with inner wall of the tube is at rest. Thank you.